Let's now work in our next topic. This is maximum and minimum values for a multivariable function. From your previous course of single variable back in your high school days and your first quarters, you know how to calculate the critical points on a single variable function. And what's that about? Well, let's work a little bit here on this graph that I'm sharing with you. Uh, we are not dealing with a 3D space or n-dimensional space. And we know, for example, that we have here this slope. The derivative is the slope of the tangent line at any point of this curve. Um, we can say that here in the top of this hill, the derivative or the partial derivative, let's say for with respect to x or with respect to y, will be zero. Okay, same case here, same case here, same case here. So whenever points the derivative of the function equals zero, then we can say that we are dealing with a critical point, either maximum or minimum. That's the case for this one, and that's the case for this one. We have four types. We have four types of critical points. Four types of critical points. One of them is the local max, which is this one over here. This is the local maximum. The absolute maximum. This is the absolute minimum. And the local minimum. This is basically the four types of critical points that we usually get out of any function. There is a special type of critical point that I'm going to highlight here, and is precisely this one. In this point, we have also the partial derivative with respect to any variable equals zero. But this is not a local max, neither an absolute max, and this is not a local minimum or an absolute minimum. This is a special case of the critical points named saddle point, or in Spanish, this is punto de silla or saddle point. So we're going to deal with these three types of critical points in this topic. Okay, so this is the, let's say, the concept or the intuitive way to start to imagine how to calculate those critical points. And why this is going to be important? Well, you decided to study engineering, And as an engineer, whatever your field of application is, even if you are not going to deal with robotics, whatever the field of engineering, you need to know this. And this is going to be part of your job because the engineer provides solutions in order to maximize or minimize or identify critical points to any variables in any model that you are working with. So as an engineer, you're working in the maquila, you're working in the food industry, in the pharmaceutical industry, in the medical industry, you will find a way or you will be required by your boss to estimate and solve problems using this approach. So let's talk a little bit about these four types of critical points. We already covered some of them here in this graph. Uh, the local maximum is when we have point a comma b in a function in a neighborhood or where this x comma y function is near. We have a local maximum if this point a comma b is greater or equal than the function f(x) of y in that neighborhood. For example, if we have this neighborhood over here, and this is equal to f(x), comma y, then we have this a comma b. Let's say this is ab here and it's in the top. So this is ab is greater or equal to all the values that covers the f(x), y around this neighborhood. If that happened, then the f evaluated at a comma b is a local maximum. Uh, the other side of the case is the number two. We have a local minimum if the values that are in that neighborhood close to this point a comma b, in this case is um, less than or equal than all the points that are nearby this f(x), y region. And this is applicable for all functions or all values of f at the points a, comma b. Now, the third case, if 1 and 2, which is this is 1 and this is 2, holds for all the points for x comma y, all the points, it means that we are, all the points is all these points from here to here and from here to there, all points, then that's the domain of the function, then f has an absolute maximum. It's absolute because in all regions across both axes of the variables, we have these critical points. Okay, this is true when, as we said, the partial derivatives with respect to the functions that we are modeling here are equal to zero. Why to zero? Because if that happens, we are having this flat line in the top of the hill. Okay. And how do we know how to calculate a saddle point? Well, we are going to share a new formula. This is a new formula for you guys. We are going to use it. Please take note of it. The formula is named the second derivatives test. Suppose that we have um, critical points that we want to know if there is a local maximum or local minimum or there is a saddle point. So let's suppose that we have the second partial derivatives. You already know what's that. Second partial derivative is when you differentiate a function with respect to x, and then if you do it again with respect to x, then you will have the second partial derivative with respect to x. So if we have those partial derivatives in the second order of f, and they are continuous on a region or a disk with a center AB, and suppose that the first derivatives are equal to 0 with respect to x and with respect to y, then we can have this new component named d, capital D. And this d is known as the determinant. And this determinant is the outcome of this second partial derivative with respect to x. So we are going to differentiate 1 and 2 times with respect to x. So the second partial derivative evaluated at points a and b times the second partial derivative with respect to y evaluated at points a and b minus the crossed partial derivative. This is you calculate the derivative with respect to x, and then the result you are going to differentiate that with respect to y, and that is going to be evaluated in the points I comma b. And this is going to be powered up to the square. So once again, the partial derivative with respect to x and then with respect to x again, evaluated at points a comma b, times the partial derivative with respect to y times again the partial derivative with respect to y evaluated at points a comma b minus the cross second partial derivative x and y to the square. If this determinant is positive, like in this case a, if the value of the determinant is positive and the partial derivative with respect to x is positive, then that critical point is a local minimum. If the determinant is positive and the partial derivative with respect to x and with respect to x is negative, then the critical point is a local maximum. If the determinant is negative, then this is not a local maximum nor local minimum, and this is considered as a saddle point. Okay. Okay, so I expect that this is clear enough for you. Let's work in the next class 1 or 2 exercises on this so we can get a more clear understanding of what we are dealing with.